Bismillahirrahmanirrahim. My dear student, I am Dr. Muhammad Yasin from Faisalabad campus. Today our topic is acidity of carboxylic acid. This topic belongs to the fundamental of organic chemistry semester 2. What we will discuss today that why carboxylic acids are acids, what is their acidity and what factors affect their acidity. So these are the key points that we are going to discuss in this lecture. On this slide, I have listed the key concepts that we will discuss today. First of all, we will discuss what are the carboxylic acids, why carboxylic acids are acidic, effect of resonance on the acidity of carboxylic acid. We will also discuss the effect of electronegative substituent and the electropositive substituent on the acidity of the carboxylic acid. So these are the key concepts that we will cover in this lecture. The carboxylic acid is an organic compound that contains a carboxyl functional group attached to an alkyl group. The general formula of carboxylic acid can be written as RCOOH. Here the R refers to the alkyl group. The carboxylic acids occur widely in nature. For example, the most important are commonly found. The natural carboxylic acid is the acetic acid, that is the active ingredient of the vinegar. All the citrus fruits contain the citric acid. All the amino acids contain the carboxylic acid functional group. Other important examples include the amino acids and fatty acids. Deprotonation of the carboxylic acids gives a carboxylate anion. Carboxylic acids can easily be synthesized through the oxidation of aldehydes. Their derivatives include esters, acid chlorides, acid anhydrides, and amides. As far as the naming of the carboxylic acids is concerned, carboxylic acids are named by replacing the E of the corresponding alkane name with the OH acid. For example, here on this slide, you may see the propanoic acid. Its name is derived from the propane, as the propanoic acid contain the three carbon atoms, and we know that the 3 carbon atoms alkene is called the propane. So from the propane name we are dropping the E and is replacing it with the oic acid. So the name becomes the propanoic acid. And if there is any substituent, you have to name that substituent you have to show that substituent with the number of the carbon atom. Remember that the carboxylic functional group is always given the number 1. So here in another example you are seeing the structure of the 4-methyl pentanoic acid. And here I have used the color scheme. You may see that the methyl is shown in the green color and it is substituted as the carbon number 4, and similarly the carboxylic functional group is present on the carbon number 1. So its name is 4-methyl pentanoic acid, since it the longest continuous chain contains the 5 carbon atom, and we know that the alkane that have the 5 carbon atom is called the pentane, and here in the name of the pentane we have dropped the E and is replaced by the oic acid. So the name of the second example here on this slide is 4-methyl pentanoic acid. Similarly, I have shown the 2 examples of the cyclic carboxylic acid. In the case of the cyclic carboxylic acid, for example, the carboxylic functional group is bonded to a ring, then the suffix carboxylic acid is used. For example, in the first example on the left side, you may see a trans 4-hydroxy cyclohexane carboxylic acid, and on the right side I have shown a cyclic carboxylic acid that is having the double bond, and the double bond location of the double bond is on the carbon number 1, and also the carboxylic functional group is present on the number 1 carbon So the example is cyclopent 1 in carboxylic acid. So you may see that in the case of the cyclic carboxyl, if the carboxylic functional group is attached to a cyclic hydrocarbon, then we are using the word carboxylic acid. Here I am not going into the detail of the nomenclature of the carboxylic acid, which indeed is not the scope of this lecture. We will discuss the acidity of the carboxylic acid. Before discussing the acidity of the carboxylic acid, I have discussed shortly about what are the carboxylic acids and how they are named. Definitely we will use the names of the carboxylic acid when we are discussing the acidity of the carboxylic acid. That's why I have shortly introduced you about the nomenclature of the carboxylic acid. Here the purpose of this slide is to introduce you the names of some of the common carboxylic acids. When a carboxylic acid loses a proton or the hydrogen atom that is attached to the carboxylic functional group, then the remaining group is called the carboxylate group, and we may also call it the acyl group. So here on this slide I have shown you the structure and the name and the name of the acyl group of some of the common carboxylic acids. For example, the first one is the formic acid. When you replace its hydrogen or when it loses the hydrogen atom, the resulting anion is called the formyl. The next one is the acetic acid. When the acetic acid loses a proton, the remaining carboxylate functional group of carboxylate anion is called the acetyl. And similarly, where the next one is the propanoic acid, or it is also called the propionic acid. Propionic acid is the common name, whereas the propanoic acid is its IUPAC name. When the propanoic acid loses one proton, the remaining anion is called the propionyl anion. Similarly, the carboxylic acid that is having the 4 number of the carbon atoms is called the butanoic acid. That is the IUPAC name, whereas its common name is the butyric acid. When the butyric acid loses a proton, the anion is called the butyryl anion. Here I have also shown you the dicarboxylic acid. Dicarboxylic acids are those carboxylic acids that have the 2 carboxylic functional groups. So the first one that I have shown is the oxalic acid. To remember the oxalic acid, malonic acid, succinic acid, glutaric acid, and adipic acid, remember the keyword OMSGA, O-M-S-G-A. So in the oxalic acid, you have just to attach the 2 carboxylic functional group with each other, and when they lose the 2 protons, the resulting anion is called the oxalyl. Whereas in the malonic acid, you have to just add one methylene group, that is the CH2 group, and in the succinic acid, you have to add another methylene group, and so on. So in the malonic acid, you may see that when the malonic acid loses the 2 protons, the resulting anion is called the malonyl anion. In the succinic acid, it is again a dioic acid, mean it has the 2 carboxylic acid functional groups. When succinic acid loses 2 protons, the resulting anion is called the succinyl anion. In the glutaric acid, when glutaric acid loses 2 protons, the resulting dianion is called the gluteryl anion. And in the adipic acid, similarly, the resulting acyl group is called the adipoyl dianion. I have similarly shown you the structure of the acrylic acid, malic acid, and fumaric acid. Remember that these malic and fumaric acid are the cis-trans isomers having the same number of carbon atoms. So only the position of the carboxylic acid in the malic acid is the cis, whereas in the fumaric acid it has the trans geometry. So these are the geometrical isomers of each other. The acyl groups of the malic and the fumaric acid, which are again the dioic acid, are called the malonyl and the fumaryl dioic acid. dianion of the malic acid is called the mallyl, whereas the dianion of the fumaric acid is called the fumaryl. Similarly, I have shown you the structure of the glycolic acid and the lactic acid as well on this slide. So these are some of the most commonly encountered carboxylic acids. I have shown you here on this slide their common name and the resulting acyl anions. Now it's proper time to discuss the acidity of the carboxylic acid. Before we discuss the acidity of the carboxylic acid, let's first discuss what kind of carbonyl oxygen is present in the carboxylic acid. Remember that the carbonyl carbon is sp2 hybridized. In the carboxylic acid, the carboxylic functional group, that is COOH, CO is the carbonyl group, and here the carbonyl carbon is sp2 hybridized. As we know that this carbonyl, the carbonyl carbon is bounded with the oxygen atom, and oxygen atom being the more electronegative than the sp2 hybridized carbon atom, and hence because of the higher electronegativity of the carbonyl oxygen, the carbonyl carbon attain the partial positive charge, and this partial positive charge has effect on the acidity of the carboxylic acid that we will discuss in the coming slides. Because of this, again, if we discuss the bond between the oxygen and hydrogen of the hydroxyl group of the carboxylic functional group, again the oxygen electronegativity of the oxygen is higher than the hydrogen, and hence the oxygen partially withdraw the electrons from the oxygen hydrogen bond, and thus producing a partial positive charge on the hydrogen atom of the carboxyl functional group, and leaving the negative partial charge on the oxygen atom of the hydroxyl group. Because of this, all the hydrogen atoms of the carboxylic acids are partially attain the partial positive charge when they are attached to the carboxylic functional group. Because of this partial positive charge on the hydrogen atom of the hydroxyl group, and partial negative charge on the carbonyl oxygen, the carboxylic acids are strongly associated with each other through hydrogen bonding, as I have shown the hydrogen bonding between the acetic acid, two molecules of acetic acid. So acetic acid, when the molecules of acetic acid exist usually in the form of a dimer unless they are diluted. Present in very low concentration. Obviously this low concentration will have effect on the hydrogen bonding, which is not beyond the scope of this lecture. However, in the solution form, acetic acid molecules usually exist in the form of a dimer, as I have shown on this slide. Hydrogen bonding, this hydrogen bonding has significant effect on the boiling point. So because of this is a very important point, my dear student, this hydrogen bonding that exists between the hydrogen atom of the hydroxyl functional group of the carboxylic functional group and the carbonyl oxygen of another carboxylic acid significantly increases its boiling point. Obviously more energy will be required to break this extra bonding, that is the hydrogen bonding, to leave the boundary of the solvent. So because of this hydrogen bonding, suppose I have in the acetic acid molecule there are two carbon atoms, and these two carbon atoms, hydrocarbon is called the alkane. If we compare its boiling point with the ethane, so it's two carbon atom hydrocarbon is called the ethane. If we compare the boiling point of the ethane with the carboxylic acid, since in the carboxylic acid, in the acetic acid, two carbon carboxylic acid is called the acetic acid, whereas the two carbon alkane is called the ethane. So when we compare the acidity of the ethane with the acetic acid, since in the acetic acid extra hydrogen bonding is present, which is not present in the case of the ethane, that's why the boiling point of the acetic acid is higher than that of the ethane. This is because of the hydrogen bonding that is present in the case of acetic acid and is not present in the case of the ethane. So remember that the hydrogen bonding that is present between the hydroxyl hydrogen and the carbonyl oxygen of carboxylic acid increases their boiling point. On this slide, I have listed the key concepts that we will discuss today. First of all, we will discuss what are the carboxylic acids, why carboxylic acids are acidic, effect of resonance on the acidity of carboxylic acid. We will also discuss the effect of electronegative substituent and the electropositive substituent on the acidity of the carboxylic acid. So these are the key concepts that we will cover in this lecture. As a result of higher electronegativity of oxygen than the hydrogen, the oxygen hydrogen bond of the carboxylate group is highly polar. So here again I am informing you that the sigma bond between of the that is present between the oxygen and the hydrogen of the hydroxyl group is highly polar because of the higher electronegativity of the oxygen than that of the hydrogen, and as a result this the hydroxyl hydrogen gets partial positive charge and the oxygen of the hydroxyl group gets the partial negative charge. Another factor that also enhances the electron withdrawing ability of the hydroxyl oxygen, the carboxylic acid, is that the hydroxyl oxygen, remember that the hydroxyl oxygen is directly attached to the carbonyl carbon, which in turn is also possessing partial positive charge. So the carbonyl oxygen is already having partial positive charge, and this carbonyl carbon have the tendency to withdraw the electrons from the other bonds. So the oxygen also have electron withdrawing ability, so it withdraws the electron from the hydrogen, and this oxygen is in turn is directly attached to an electron deficient carbon atom, which is in turn attached to the carbonyl oxygen, which is also have the partial negative charge. So all these two factors, number one, the electron withdrawing ability of the oxygen of the hydroxyl group, and as well as the electron withdrawing ability of the carbonyl carbon. It attains the electron withdrawing ability because of the carbonyl oxygen. So the hydroxyl hydrogen, the sigma bond of the hydroxyl group, that is the bond between the oxygen and hydrogen, is highly polar. And here I have shown you this bond with a red line, and I have shown you that the hydrogen is possessing the partial positive charge and the oxygen is possessing the partial negative charge. As a result, sigma bond between the oxygen and the hydrogen of the hydroxyl group is highly polar, and consequently the attached hydrogen can easily be released, thus generating an anion called the carboxylate anion. So here I have shown you an equilibrium between the carboxylic acid and its resulting anion, or the carboxylate anion. So because of the highly non-polar nature of the sigma bond that is present between the hydroxyl oxygen and the hydrogen, this bond is liable or can easily be broken, and thus generating a proton and a carboxylate anion. And any species that produce the proton or can donate the proton, we say it a acid. That's why the carboxylic acids are acid, because they donate the proton. If they have one carboxylic functional group, they will donate one proton. If they have more than one, they will donate more than one hydrogen per molecule. Here I have shown you monocarboxylic acid, and hence it is donating one molecule of the carboxylic acid is donating one proton. The next question is, how strong are these acids? What is the acidity strength of these carboxylic acids? So let's discuss how strong carboxylic acids are. As far as the naming of the carboxylic acids is concerned, carboxylic acids are named by replacing the E of the corresponding alkane name with the OH acid. For example, here on this slide, you may see the propanoic acid. Its name is derived from the propane, as the propanoic acid contain the three carbon atoms, and we know that the three carbon atoms alkene is called the propane. So from the propane name we are dropping the E and is replacing it with the oic acid. So the name becomes the propanoic acid. And if there is any substituent, you have to name that substituent with the, you have to show that substituent with the number of the carbon atom. Remember that the carboxylic functional group is always given the number 1. So here in another example you are seeing the structure of the 4-methyl pentanoic acid. Here I have used the color scheme. You may see that the methyl is shown in the green color and it is substituted at the carbon number 4, and similarly the carboxylic functional group is present on the carbon number 1. So its name is 4-methyl pentanoic acid, since it the longest continuous chain contains the 5 carbon atom, and we know that the alkane that have the 5 carbon atom is called the pentane, and here in the name of the pentane we have dropped the E and is replaced by the oic acid. So the name of the second example here on this slide is 4-methyl pentanoic acid. Similarly, I have shown the 2 examples of the cyclic carboxylic acid. In the case of the cyclic carboxylic acid, for example, the carboxylic functional group is bonded to a ring, then the suffix carboxylic acid is used. For example, in the first example on the left side, you may see a trans 4-hydroxy cyclohexane carboxylic acid, and on the right side, I have shown the a cyclic carboxylic acid that is having the double bond, and the double bond location of the double bond is on the carbon number 1, and also the carboxylic functional group is present on the number 1 carbon. So the example is cyclopent 1 in carboxylic acid. So you may see that in the case of the cyclic if the carboxylic functional group is attached to a cyclic hydrocarbon, then we are using the word carboxylic acid. Here I am not going into the detail of the nomenclature of the carboxylic acid, which indeed, if we compare the carboxylic acids with the mineral acids like hydrochloric acid, nitric acid, sulfuric acid, remember carboxylic acids are much weaker acid than the mineral acids, but much stronger acid than alcohol, since alcohols also have hydroxyl functional group, and as I have informed you that in the case of a hydroxyl functional group, the bond between the oxygen and the hydrogen of the hydroxyl group is polar. Then why not we say that the alcohols are not the acid, whereas carboxylic acids are the acid? Remember that the alcohols also have acid character, but the resulting alkoxy ion. Here I have shown you the ethyl alcohol. When ethyl alcohol loses a proton, the resulting anion is called ethoxy. And in the general, if you speak generally, when a alcohol that is represented with ROH loses a proton, the resulting anion, that is RO -1, is called alkoxy. Remember that in the case of the carboxylic acid, the carboxylate anion show resonance. The negative charge of one oxygen is present on the hydroxyl oxygen as well as on the carbonyl oxygen. So this is resonating between this. In the case of the carboxylic acid, the resulting anion is resonance stable, and the resulting negative charge is resonating on the 3 atoms. That is, two are the oxygen atom and one is the carbon atom of the carbonyl functional group. Whereas in the alkoxy group, the negative charge is localized, and hence the alkoxy group is less stable than the carboxylate functional group, and hence that's why the carboxylic acids can lose a proton, since their resulting anion is more stable than the alkoxy anion of the alcohol. That's why these alcohols don't lose the proton. However, under very hard conditions, alcohols also behave like acid, but their acidity is much more less than the carboxylic acid, which are in turn much more less acidic than the mineral acids. So this sequence you have to remember. Again, here on this slide I have shown, I have elaborated why alcohols are less acidic than the carboxylic acid. If an alcohol donates a proton due to the polarity of the sigma bond between the oxygen and the hydrogen bond and the hydrogen atom of the hydroxyl group, the resulting anion is called the alkoxy anion. Similarly, if a carboxylic acid donate a proton due to the polarity of the sigma bond between the oxygen and the hydrogen, of the hydroxyl group, the resulting anion is called the carboxylate anion. If we compare the stability of the two anions, I have compared the relative stability of the two, that is the alkoxy and the carboxylate anion, on the next slide. So let's move towards the next slide. Here on this slide, on the top, you may see a carboxylic acid that is reacting, that is actually losing a proton, so thus generating a carboxylate anion. And in the second line, you may see that this negative charge on the carboxylate anion is resonating between the two oxygen atoms, and hence involving, since this resonance takes place through the carbonyl carbon, so we may say that in the case of the carboxylate anion, the charge is resonating between the three atoms, that is the two oxygen and one the carbon atom. Whereas in the case of the alcohol, when it lose, anyhow, if it lose a proton, the resulting alkoxy ion do not have resonance. That's why we say that because of the higher stability of the carboxylate anion than the alkoxy ion, we say that the carboxylic acids are much more stronger acids than the alcohol. Here at the bottom of this slide, I have shown some pK value. For example, ethyl alcohol, I have a pK value of 60. Whereas the pK value of the phenol, that is also an alcohol, but it is an aromatic alcohol, since in the case of the phenol, the negative charge is delocalized on the benzene ring, so its pK value is higher than that of the ethyl alcohol. And similarly, the pK value of the acetic acid is 4.76, and that of the HCl is -7. So if I compare the acidic strength of the acetic acid and the phenol, acetic acid, the resulting anion of the acetic acid is the acetate ion. And in the case of the acetate ion, there are two resonance structures possible, whereas in the case of the phenol, when it loses one proton, the resulting phenoxyanion have more than one resonance structure. You may draw it. Then why? As we know that as the number of the resonance structure increases, the stability of the that molecule also increases. So in the case of the phenol and acetic acid, the anion of the acetic acid is showing the two-part resonance structure, whereas in the case of the phenoxyanion, we have more than one resonance structure. Then why acetic acid is stronger than the phenol? On the basis of the resonance structure, the phenol should be much more stronger acid than the acetic acid. Why? My question is why? Let's discuss it or explain it in the coming section. Another factor that determines the relative higher acidic strength of the carboxylic acid than the alcohol is the energy of formation of the carboxylate and the alkoxyanion. Here on this slide, you may see when carboxylate loses a proton, it has to overcome an energy that is I have represented with this delta G naught, and in the case of the alkoxyanion, this energy is much higher than the energy of formation of the carboxylate anion. So the energy of formation of the alkoxy anion is higher than that of the carboxylate anion. That's why the carboxylate loses the anion more easily than the alkoxy anion. Here's the detailed explanation why phenol less acidic than the acetic acid, although the number of the resonance structure of the phenoxyanion is higher than the acetic anion. The answer is the negative charge on more electronegative atom is more stable than the less electronegative atom. So in the case of the acetic acid, the resulting acetate anion is resonance stabilized, and In the case of the acetate anion, the negative charge is resonating on the hydroxyl oxygen and on the carbonyl oxygen, which I have shown in the blue and red colors respectively. Whereas in the case of the phenol, when it loses a proton, the resulting phenoxyanion, the negative charge of the resulting phenoxyanion is resonating on the phenyl ring, and in the phenyl ring you may know that it is composed of the carbon atoms, and the negative charge is resonating on the carbons of the phenyl ring. So in the case of the acetate anion, the negative charge is resonating on the oxygen atoms. Since oxygen atom is more electronegative than the carbons of the phenyl ring, so acetate anion is more stable than the phenoxyanion, and hence acetic acid is more stable, more acidic than the phenol. If we compare the carboxylic acids with the mineral acids like hydrochloric acid, nitric acid, sulfuric acid, remember carboxylic acids are much weaker acid than the mineral acids, but much stronger acid than alcohol, since alcohols also have hydroxyl functional group. And as I have informed you that in the case of a hydroxyl functional group, the bond between the oxygen and the hydrogen of the hydroxyl group is polar. Then why not we say that the alcohol, any factor that destabilize the carboxylate anion relative to the undissociated carboxylic acid will decrease the acidity of the carboxylic acid. Electron withdrawing groups attached to the carboxylic acid will increase the acidity, and electron donating groups will decrease the acidity of the carboxylic acid. Any factor that will increase the resonance of the carboxylate anion will increase the acidic strength of the carboxylic acid. My question is, why is trifluoroacetic acid 32 times more stronger than the acetic acid? Electron withdrawing or donating process through a sigma bond by an atom by virtue of the difference in the electronegativity of the bonded atom is called inductive effect. Inductive effect is of two types. Electron withdrawing atoms of the substituent create the negative inductive effect, which is mostly written as I negative effect, and the electron donating atoms or the substituent create the positive inductive effect, which is mostly written as I positive effect. Inductive effect is a distance dependent property. Here is the magnitude of the negative inductive effect, greater will be increased in the acidity and vice versa. As the number of the substituent having negative inductive effect increases, acidity of the carboxylic acid increases and vice versa. Here I am comparing the acidic strength of the trichloroacetic acid, dichloroacetic acid, chloroacetic acid, and acetic acid. The most acidic among these carboxylic acid is the trichloroacetic acid, which is having the 3 chloro substituent, which produce much more negative inductive effect, and hence they polarize the hydroxyl sigma bond, that is the bond between the oxygen and the hydrogen of the hydroxyl bond, and it is now more easily liable than in the case of acetic acid. So in the case of trichloroacetic acid, the magnitude of the negative inductive effect is higher than in the case of the chloroacetic acid. So the trichloroacetic acid is the more powerful, or you may say that it is 32 times more stronger than the acetic acid by the virtue of the negative inductive effect that is produced by 3 chloro substituent. Inductive effect depends on the distance. Less is the distance of the electron withdrawing substituent from the carboxylate group, greater will be the increase in the acidity. For example, 2-chlorobutanoic acid is stronger acid than the 3-chlorobutanoic acid, because in the case of the 2-chlorobutanoic acid, the chloro substituent is nearer to the carboxylate substituent, whereas in the case of 3-chloro substituent, the chloro substituent is relatively far from the carboxylate substituent. And similarly, in the case of 4-chlorobutanoic acid, 4-chlorobutanoic acid is much weaker than the 3-chlorobutanoic acid, because in the 4-chlorobutanoic acid, the chloro substituent is is on the farthest position than the 2-chloro-butanoic acid. So you may say that in this series the butanoic acid is the weakest acid, whereas the 2-chloro-butanoic acid is the powerful or the more acidic than the butanoic acid because of the inductive effect. Here you may see that as the position of the electron withdrawing substituent, that is the chloro substituent, increases from the carboxylate functional or the carbonyl position, the acidity also decreases. You may see that the pK value of the butanoic acid is 4.82, whereas that of the 1-chloro-butanoic acid is 2.86. So at the end, this is the summary of the today's lecture. Acidity of the carboxylic acid depends on the bond polarity of the sigma bond between the hydrogen atom and the oxygen atom of the hydroxyl group. Acidity of the carboxylic acid depends upon the relative stability of the carboxylate anion. Acidity of the carboxylic acid depends on the inductive effect of the substituent. Those substituents that create the negative inductive effect increase the acidity, and positive inductive effect decrease the acidity of the carboxylic acid. Now it's the time for the quiz. You have to arrange you have to give the reason why the pK value of the para-methoxybenzoic acid is 4.46, whereas the benzoic acid the pK value is 4.19, and for the para-nitrobenzoic acid the pK value is 3.41. So you may say that the para-nitrobenzoic acid is the strongest acid among these three benzoic acid derivatives. You have to give the reason why para-nitrobenzoic acid is stronger acid than the para-methoxy and para-methoxybenzoic acid and the benzoic acid alone. There is a hint. You have to explain it on the basis of the inductive effect. The second assignment is which acid of each phase would you expect to be stronger in acidic strength and why? For example, you have to compare the acidic strength of the acetic acid and fluoroacetic acid. You have to compare the acidic strength of the 2-fluoro-butanoic acid and 3-fluoro-butanoic acid. The third question is arrange the following compounds in the increasing order of their acidic property along with the reason. You have to arrange give the order of the acidity of the benzoic acid, 4-nitrobenzoic acid and 3,4-dinitrobenzoic acid and 4-methoxybenzoic acid. At the end, here is a list of the recommended books that you may consult for the preparation of your lecture.